Welcome to this problem-solving session. In this video, we'll dive into problem number 164, titled Maximum Gap. This problem challenges us to find the largest gap between consecutive elements in an unsorted array. We'll explore various approaches, analyze their efficiency, and learn key techniques that can be applied to similar scenarios. Let's get started. The goal of this problem is to find the maximum gap between successive elements after sorting an array of integers, nums. For example, if the input array is 3, 6, 9, 1, we sort it into 1, 3, 6, 9, and calculate the gaps between consecutive elements. The largest gap among these is the answer, which in this case is 3. However, there are some constraints. If the array has less than 2 elements, the result is 0 since no gap can exist. Additionally, the problem requires that the solution runs in linear time, O(n), and uses O(n) extra space. This means you cannot rely on standard sorting algorithms like quicksort or mergesort, which are O(n) log n. Instead, you need to think about specialized techniques to achieve the required efficiency. To help clarify the problem, let's look at some examples. In the first example, the input is 3, 6, 9, 1. After sorting, the array becomes 1, 3, 6, 9. The differences between adjacent elements are 3, 1 equals 2, 6, 3 equals 3, and 9, 6 equals 3. The largest of these gaps is 3, so that is the output. In the second example, the input is 10. Since there is only one element, there are no successive elements to calculate a gap, and the output is 0. This highlights that the algorithm must handle arrays with fewer than 2 elements gracefully, returning 0 in such cases. Now consider the third example, where the input is 1, 10 million. With only 2 elements in the array, the maximum gap is simply the absolute difference between them, which is 1,000,000,000,1 equals 9999999. This example illustrates that the algorithm must handle arrays with large numbers efficiently, as the maximum value of an element can go up to 10⁻⁹. Looking at the constraints, the array can have up to 10⁻⁵ elements, and the solution must run in O(n) time. It's also important to consider edge cases, such as arrays with only one element, arrays containing duplicate numbers, or arrays with a wide range of values. These constraints mean you'll need to design your algorithm carefully to ensure it's both correct and efficient. When tackling the maximum gap problem, several approaches can be considered. The brute force method is a simple and direct solution. You sort the array and then calculate the maximum difference between consecutive elements in this sorted array. However, sorting dominates the time complexity, making it O(n) log n, which violates the problem's requirement for an O(n) solution. Because of this, the brute force approach, while intuitive, is not feasible. To meet the O(n) time constraint, we can use an optimized approach based on bucket sort. This technique leverages the pigeonhole principle. By dividing the range of numbers into n1 buckets, where n is the size of the array, we can represent different ranges of numbers efficiently. The bucket size is calculated using the formula, ceiling of max min /n1. With this setup, the key insight is that the maximum gap will always occur between numbers in different buckets, not within the same bucket. This simplifies the problem significantly. To implement this, the first step is to find the array's minimum and maximum values, and if the array has fewer than 2 elements, there's no gap to compute, so we return 0. Next, we calculate the bucket size and create n1 buckets. Each number is then placed into its respective bucket based on its value. While doing so, we track the minimum and maximum values within each bucket. Finally, we iterate through these buckets to calculate the gaps between their boundaries. Once the buckets are populated, the gap between successive buckets is calculated by comparing the maximum value of the current bucket to the minimum value of the next non-empty bucket. By doing this for all the buckets, we identify the largest gap, which is then returned as the result. This approach achieves the desired O(n) time complexity. Each number is processed in constant time during placement, and since we only iterate through the buckets a fixed number of times, the performance remains efficient. The bucket sort technique was chosen because it meets the constraints of O(n) time complexity and uses O(n) extra space. This method takes advantage of the properties of buckets and their ranges to pinpoint the maximum gap efficiently without sorting the array. One of the key insights in this strategy is recognizing that the largest gap will always occur between buckets, not within a single bucket. By dividing the range into n1 buckets, we ensure that at least one bucket will remain empty if the numbers are evenly distributed. This guarantees that the largest gap lies between buckets, simplifying the problem further. When comparing approaches, it's clear that the brute force method, while simpler to implement, fails to meet the time complexity constraint due to its reliance on sorting. On the other hand, bucket sort achieves the required efficiency with a small trade-off and additional space for storing the buckets. Other alternatives, such as radix sort, could also work in linear time for integer inputs. However, bucket sort aligns well with the problem's constraints by focusing on the gaps between successive numbers, making it a more intuitive choice. In conclusion, bucket sort strikes the right balance between simplicity and efficiency, making it the most suitable strategy for solving the maximum gap problem effectively. To solve the maximum gap problem, we're tasked with finding the largest gap between consecutive elements in the sorted order of an unsorted array. The challenge here is that we need to achieve this in linear time complexity, O(n), without explicitly sorting the array. To meet this requirement, we use a strategy called bucket sorting. First, it's important to clearly define the problem. We are looking for the largest difference between successive numbers as if the array were sorted, but sorting directly would violate the time complexity constraint. Next, we must handle edge cases. If the array has fewer than 2 elements, there are no successive numbers, so the maximum gap is 0. Similarly, if all elements in the array are identical, the gap remains 0. Once edge cases are addressed, we compute the range of values by finding the minimum and maximum numbers in the array. If the difference between the maximum and minimum is 0, it means all numbers are the same, and again, the maximum gap is 0. These steps set the foundation for the bucket-based solution. After defining the problem and handling edge cases, the next step is to divide the range of values into buckets. First, we determine the bucket size using the formula bucket_size equals max, 1, max_vel, min_vel, / n1, where n is the size of the array. This ensures that the bucket size is large enough to minimize the total number of buckets while maintaining efficiency. Then, we calculate the total number of buckets as bucket_count equals max_vel, min_vel, / bucket_size plus 1. Once we have the buckets, we initialize them. Each bucket will store 2 pieces of information, the smallest element in the bucket, called bucket_min, and the largest element in the bucket, called bucket_max. Initially, bucket_min is set to infinity, and bucket_max is set to -infinity. Now, we distribute the elements of the array into these buckets. For each number in the array, we calculate its bucket index using number min_vel, / bucket_size and update the corresponding bucket_min and bucket_max values. This step ensures that all elements are placed in their appropriate buckets while preserving the linear time complexity requirement. Once all elements are placed into their respective buckets, we can compute the maximum gap by scanning the buckets. We start by initializing the max_gap variable to 0 and previous _max to the minimum value of the array, min_vel. Then, we iterate through the buckets in order. If a bucket is empty, meaning its bucket_min is still infinity, we simply skip it. For non-empty buckets, we calculate the gap between the previous _max and the bucket_min of the current bucket. If this gap is greater than the current max_gap, we update max_gap. After calculating the gap, we update previous _max to the bucket_max of the current bucket. This way, we ensure that we are always comparing the maximum value of the previous bucket with the minimum value of the current bucket. Once all buckets have been scanned, the max_gap will hold the largest difference between successive elements in the sorted order. Finally, we return this value as the result. Buckets are central to this solution because they allow us to partition the range of values into smaller intervals. This localization makes it possible to calculate the maximum gap without explicitly sorting the array. Successive elements in the sorted order will always belong to adjacent buckets, so empty buckets can safely be ignored, as they don't contribute any valid elements. The choice of bucket size is also critical. Using the formula bucket underscore size equals max underscore vel min underscore vel / n1 ensures that the average number of elements per bucket is constant, which is essential for maintaining O(n) time complexity. Edge cases, such as arrays with duplicate values, very small arrays, or cases where all elements fall into a single bucket, are all handled explicitly by the algorithm. Finally, the buckets themselves are simple data structures, each storing just two values, bucket underscore min and bucket underscore max. By scanning the array once for bucket placement and performing a second pass to calculate the maximum gap, the algorithm achieves both simplicity and efficiency. This algorithm is optimized to avoid sorting altogether by leveraging the properties of buckets to achieve linear scalability. The bucket operations themselves are efficient because each element is processed with a constant number of operations. This ensures that the algorithm remains performant even for very large inputs. In terms of complexity, the time complexity is O(n), because we perform a fixed amount of work for each element in the array. The space complexity is also O(n), due to the additional storage required for the buckets. These optimizations make the algorithm both practical and scalable, especially for scenarios where sorting the array is computationally expensive. By focusing on minimizing the number of operations and ensuring that the bucket size is chosen optimally, the algorithm achieves a perfect balance of efficiency and correctness. In this implementation, we start by defining the maximum gap function inside the solution class. The first thing we do is check if the input list nums has fewer than two elements. If it does, we immediately return 0 since no gap can exist. Next, we calculate the minimum and maximum values in the array using Python's built-in min and max functions. These values will help us determine the range of the data. We then calculate the bucket size, which is the maximum of 1 or the integer division of the range divided by the number of gaps, that is, n1. This ensures that the bucket size is at least 1. Based on this bucket size, we compute the total number of buckets needed, which is determined by dividing the range by the bucket size and adding 1. After that, we initialize our buckets as a list of pairs, where each pair holds the minimum and maximum value for a particular bucket. Initially, each bucket's minimum is set to positive infinity, and the maximum is set to negative infinity. Then, we iterate through each number in the input array, determine which bucket it belongs to using the formula number min underscore vel / bucket underscore size, and update the corresponding bucket's minimum and maximum values accordingly. Once all the numbers are placed into their respective buckets, we calculate the maximum gap. We initialize max underscore gap to 0 and use a variable prev underscore max to track the maximum value from the last non-empty bucket, starting with the minimum value of the array. Then, we iterate through each bucket. If a bucket is empty, that is, its minimum value is still set to positive infinity, we skip it using a continue statement. For non-empty buckets, we calculate the gap between the minimum value of the current bucket and the prev underscore max value. This gap is compared to the current max underscore gap, and we update max underscore gap if the new gap is larger. Finally, we update prev underscore max to the maximum value of the current bucket, preparing it for the next iteration. Once all buckets have been processed, we return max underscore gap, which represents the largest gap between consecutive numbers in the sorted form of the array. Here, we begin the Java implementation of the maximum gap problem. First, we handle the edge case where the input array is null or has fewer than two elements. In such cases, we simply return 0, as no gap can exist. Next, we proceed to find the minimum and maximum values in the array. This is done using a simple loop where we iterate through each number and update our minimum and maximum variables accordingly. Once we have the minimum and maximum values, we calculate the bucket size and the total number of buckets. The bucket size is determined as the maximum of 1 and the integer division of the range between the maximum and minimum values by the number of gaps, which is 1 less than the length of the array. Using this bucket size, we calculate the number of buckets needed to cover the range by dividing the range again by the bucket size and adding 1. Finally, we initialize the buckets as a two-dimensional array where each bucket will track the minimum and maximum values it contains. Initially, we set the minimum values to integer.max underscore value and the maximum values to integer.min underscore value, indicating that the buckets are empty. Once the buckets are initialized, we proceed to place the numbers into their respective buckets. For each number in the input array, we determine its bucket index using the formula based on its position relative to the minimum value and the bucket size. We then update the corresponding bucket's minimum and maximum values. After placing all the numbers into buckets, the next step is to calculate the maximum gap. We initialize the maximum gap to 0 and set a variable, prevmax, to the minimum value of the array. Then, we iterate through each bucket. If a bucket is empty, we skip it. For non-empty buckets, we calculate the gap between the previous bucket's maximum value and the current bucket's minimum value, updating the maximum gap if this value is larger. We then update prevmax to the maximum value of the current bucket. Once all buckets are processed, we return the maximum gap as the result. This technique ensures that we achieve efficient computation while maintaining the correctness of the solution. To solve the problem of finding the maximum gap between elements in a sorted form of the array, we start by analyzing the input array nums equals 3, 6, 9, 1. The first step is to determine the minimum and maximum values, which are min_val equals 1 and max_val equals 9. With 4 elements in the array, we calculate the bucket size and the number of buckets. The bucket size is computed as max 1, 9 to 1, // 4 to 1, which simplifies to max 1, 8 / 3, and evaluates to 2. The bucket count is determined as 9 to 1, // 2 plus 1, resulting in 4 buckets. Next, we initialize these buckets, each represented as a pair, INF, to track the minimum and maximum values within that bucket. Now, we place each number into its corresponding bucket based on the formula IDX equals number min_val / bucket _size. For number equals 3, the index is calculated as 3 to 1 / 2 equals 1, so the second bucket updates to 3, 3. Similarly, number equals 6 places it in the third bucket, updating it to 6, 6. The number 9 falls into the fourth bucket, updating it to 9, 9. And 1 goes into the first bucket, updating it to 1, 1. At the end of this step, the buckets are 1, 1, 3, 3, 6, 6, 9, 9. With the numbers placed in their respective buckets, we now calculate the maximum gap. We initialize max_gap as 0 and set prev_max to the minimum value, 1. As we iterate through the buckets, we calculate the gap between the minimum value of the current bucket and prev_max, updating max_gap whenever this gap is larger than the current value of max_gap. Starting with the first bucket, 1, 1, we skip it as it's not empty, and prev_max remains 1. For the second bucket, 3, 3, the gap is calculated as 3, 1 equals 2, so max_gap is updated to 2, and prev_max becomes 3. The third bucket, 6, 6, gives a gap of 6, 3 equals 3, further updating max_gap to 3, and prev_max is now 6. Finally, the fourth bucket, 9, 9, results in a gap of 9, 6 equals 3, but max_gap remains 3 as the gap is not larger. After iterating through all the buckets, the final maximum gap is determined to be 3. Now consider a new example with nums equals 10, 1, 100, 50. First, we determine the minimum and maximum values, min_val equals 1 and max_val equals 100, and calculate the bucket size and count. The bucket size is max 1, 100 to 1, // 4 to 1, which simplifies to max 1, 99 / 3, and evaluates to 33. The bucket count is 100 to 1, // 33 plus 1, resulting in 4 buckets. These buckets are initialized as INF. Next, we distribute the numbers into their respective buckets. For number equals 10, the index is 10 to 1 / 33 equals 0, so the first bucket updates to 10, 10. The number 1 also falls into the first bucket, updating it to 1, 10. For 100, the index is 100 to 1 / 33 equals 3, placing it in the fourth bucket as 100, 100. Finally, 50 goes into the second bucket with an index of 50 to 1 / 33 equals 1, updating it to 50, 50. After placing all the numbers, the buckets are 1, 10, 50, 50, INF, 100, 100. With the buckets populated, we calculate the maximum gap for nums equals 10, 1, 100, 50. We initialize max_gap as 0 and prev_max as 1. Iterating through the buckets, we begin with 1, 10, skipping it as it's not empty, and prev_max remains 10. Moving to 50, 50, we compute the gap as 50, 10 equals 40, updating max_gap to 40, and set prev_max to 50. The third bucket, INF, is empty, so we skip it. Finally, the fourth bucket, 100, 100, gives a gap of 100, 50 equals 50, updating max_gap to 50, and prev_max is set to 100. After iterating through all buckets, the final maximum gap is found to be 50. In the last example, we examine nums equals 1, 1, 1, 1. Here, the minimum and maximum values are both 1, and the length of the array is 4. The bucket size is calculated as max, 1, 1 to 1, // 4 to 1, which simplifies to 1. The number of buckets is 1 to 1, // 1 plus 1 equals 1. We initialize a single bucket as INF. Since all numbers in the array are 1, they all fall into the same bucket. Using the formula IDX equals number min_vel / bucket _size, the index for all nums is 0, so the bucket updates to 1, 1. At the end of this step, the final buckets are 1, 1. Finally, we calculate the maximum gap for nums equals 1, 1, 1, 1. We initialize max_gap as 0 and prev_max as 1. As we iterate through the buckets, the single bucket, 1, 1, is not empty, but there's no gap between its minimum value and prev_max. Since all numbers are identical, no gap exists between any two values, and the maximum gap remains 0. Thus, the final output is 0. The time complexity of this solution can be broken down into several steps. First, finding the minimum and maximum values in the array involves traversing all the elements once. This gives us a time complexity of O(n) for these operations. Next, calculating the bucket size and the number of buckets involves straightforward arithmetic operations, which are constant time, or O(1). Then, we need to initialize the buckets. Since the number of buckets is proportional to the size of the array in the worst case, this step requires O(n) time as well. Lastly, placing each number into its respective bucket involves determining the index for each number and updating the bucket's minimum and maximum values, both of which are constant time operations. Since we perform these steps for all n numbers, this part also has a time complexity of O(n). After placing the numbers into buckets, the next step is to find the maximum gap between the buckets. This involves iterating through all the buckets to compute the gap between consecutive non-empty buckets. Since the number of buckets is proportional to the size of the array, this step takes O(n) time in the worst case. When we add up all the steps, the overall time complexity of the algorithm is O(n) for finding the minimum and maximum values, O(1) for calculating the bucket size and count, O(n) for initializing the buckets, O(n) for placing the numbers into buckets, and O(n) for finding the maximum gap. Combining these, the total time complexity remains O(n), meaning the algorithm runs in linear time. Now let's analyze the space complexity of this algorithm. The main space usage comes from the buckets. In the worst case, when all elements in the array are distinct, the number of buckets is proportional to the size of the array. Each bucket stores just two values, the minimum and maximum. So, the space required for the buckets is O(2) bucket_count, which simplifies to O(n). Additionally, the algorithm uses a small, constant amount of space for auxiliary variables like the minimum and maximum values, the bucket size, and others. These contribute only O(1) to the total space complexity. When we combine these, the overall space complexity is O(n), dominated by the space required for the buckets. Let's compare this bucket-based approach to the brute force approach. A naive way to solve this problem would be to sort the array first and then calculate the gap between consecutive elements. Sorting the array takes O(n) log n time, and calculating the gaps takes O(n) time, so the total time complexity of the brute force approach is O(n) log n. In terms of space, the brute force approach uses O(1) space if sorting is performed in place, or O(n) space if a new sorted array is used. On the other hand, the bucket-based approach improves the time complexity to O(n) by eliminating the need for sorting. However, it requires O(n) additional space for the buckets. This trade-off highlights the advantage of the bucket-based approach in terms of time efficiency, especially for large datasets. Finally, let's discuss the best, average, and worst-case scenarios for this algorithm. In the best case, where all elements in the array are the same, the algorithm still operates in O(n) time because it needs to traverse the array and initialize the buckets. In the average case, the numbers are distributed evenly across the buckets, and the algorithm performs O(n) operations. In the worst case, where all elements are distinct, the number of buckets is proportional to the size of the array. Even in this scenario, the algorithm processes each element a constant number of times to place it in a bucket and compute the gap. This ensures that the time complexity remains O(n). The space complexity is also O(n), dominated by the buckets. Overall, the algorithm maintains its efficiency across all cases, making it well suited for this problem. When solving the maximum gap problem, it's essential to watch out for some common mistakes that can trip you up. First, forgetting to handle edge cases like an empty array or an array with just one element can lead to runtime errors. Always make sure your solution explicitly accounts for these scenarios. Next, when dealing with large inputs in languages like Java or C++, be cautious of integer overflow. This is particularly important when calculating gaps or differences between numbers. Another frequent issue is assuming the input is already sorted. Beginners often overlook this, leading to incorrect calculations. Always validate your assumptions about the data. Additionally, if you're implementing a bucket sort solution, ensure the bucket size and number of buckets are calculated properly. Misconfiguring these can result in inaccurate results. Finally, relying on a sorting-based solution for very large arrays might seem simple but can be computationally expensive. For such cases, exploring an O(n) approach like bucket sort can significantly improve performance. For interviews, the maximum gap problem offers a great opportunity to showcase your problem-solving skills. Interviewers often emphasize the importance of optimal solutions, especially when working with large inputs. While it's okay to start with a brute force approach to demonstrate your thought process, you should be ready to explain and implement more efficient solutions, such as bucket sort or radix sort. It's also crucial to clearly articulate the time and space complexities of each approach you discuss. For instance, a sorting-based solution has a time complexity of O(n) log n, while bucket sort can achieve O(n) under certain conditions. Another key angle in interviews is recognizing patterns. This problem involves finding maximum differences, gaps, or intervals, a pattern that appears in various other challenges. Identifying this pattern can help you draw connections to similar problems, making it easier to apply appropriate techniques in different scenarios. The techniques used in maximum gap are closely related to a number of other problems on LeetCode. For example, in LeetCode 41, first missing positive, you can use bucket-based or in-place manipulation techniques to find the smallest missing positive integer. Similarly, in LeetCode 268, missing number, the focus is on identifying a single missing element in a sequence, which also ties into gap-related logic. The maximum gap problem itself is a canonical example for applying bucket sort in calculating maximum differences, so a deep understanding here can enhance your ability to solve similar challenges. Another related problem is LeetCode 448, find all numbers disappeared in an array, which involves manipulating arrays efficiently to discover missing numbers. Recognizing how these problems share underlying principles can help you build a stronger intuition for tackling a variety of array-based challenges. There are several approaches to solving the maximum gap problem, each with its own trade-offs. The brute force approach involves sorting the array and calculating the gaps between consecutive elements. It's simple to implement, but the time complexity is O(n) log n, which might not be ideal for very large inputs. A more efficient option is bucket sort. This leverages the idea of grouping numbers into ranges, allowing you to find the maximum gap in O(n) time. However, this approach requires careful handling of edge cases and proper calculation of bucket sizes to ensure accuracy. Another alternative is radix sort, which is also an O(n) solution and avoids some of the floating point precision issues that bucket sort might encounter. That said, radix sort can be more complex to implement in certain scenarios. Understanding these trade-offs is key to selecting the right approach based on the problem's constraints and requirements. Great job! To sum up, we tackled the maximum gap problem and explored efficient techniques to solve it. Remember, leveraging the right tools, such as bucket sort, can make all the difference in performance. Thanks for watching, and don't forget to like and subscribe for more problem-solving sessions. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!